Hey everyone, Mr. Fritz here. We are going to talk about logarithms. And to do so, let's start off by thinking about something other than logarithms. Let's start off by thinking about square roots. I'm going to build you a mental bridge from square roots to logarithms. And hopefully this will kind of help you to envision how we figure out what these logarithms actually represent and are equal to. Think about how you find square roots. If I have these lists of square roots, you have a way of figuring out what they're equal to. And really what you're doing, as my turtle friend here is demonstrating, is you're thinking, what squared equals 144? You don't really have a way of calculating this in your mind, but you're thinking, well, I know that 12 squared equals 144, so that means that the square root of 144 must be 12. And you're thinking the same thing with the square root of 9. I know that 3 squared is 9, so this has got to equal 3. But then you look at something like the square root of 23, and right off the bat, we know that there's not a nice integer number that squares to get you to 23. And so at this point, you probably do a little bit of estimation in your head. You think, well, this is between 16 and 25. So you're thinking, well, this must be between about 4 and 5. So maybe this is like about 4.5. And you can check on your calculator, see what a better approximation is. But this is kind of what we're thinking when we're thinking about square roots. We're not actually calculating in our minds what the number is. We're really thinking about the reverse operation, which would be squaring. Consider this last example, the square root of negative 81. If you were to put aside all complex and imaginary numbers, we would say, nope, can't do this because a negative value cannot be square rooted. So there are, even in square roots, some numbers that you're not really supposed to put inside of the square root. So keep this in mind as we talk about logarithms, where we're not actually thinking about how to calculate these in our mind, but we're thinking about the reverse operation, which is in this case squaring. If we talk about what logarithms are, let's talk about a definition first. A definition is, a logarithm is a quantity representing the power to which a fixed number, the base, must be raised to produce a given number. And here's the key piece here. It is the inverse of the exponential function. So just as square roots are the inverses of squaring, logarithms are the inverse of exponentials. So keep that in mind. So we have two different forms here, logarithmic form and exponential form. If I have some log, we say that this b is the base, the a is the input, and the c would be the output. We can rewrite this in exponential form as b, same base, raised to the c power equals a. So what you can see here is that the a's and the c's have kind of swapped inputs and outputs. In exponential form, the input, this would be your input here. And this would be your output here. So we have switched the positions of the inputs and outputs for logarithmic form. And really, if you can keep in mind here that a logarithm equals the exponent, then that'll kind of help you visualize this thing. So let me give you an example with numbers. If I have log base 2 of 8, that is equal to 3. This is the exponent that, when written in exponential form, will give you the input. So just like with square roots, we're not actually thinking about, I'm not calculating in my mind anything that gets me from 2 to 8, but what I'm thinking is, what do I have to raise 2 up to in order to get 8? So we kind of have to think exponentials in order to evaluate these logarithms. So let's talk about just the standard logarithm. If you see a log that does not have a base, then the standard logarithm is base 10. And so now for these four examples, we have to think about what the values of these things will be, and the base of all of them is 10. Some of them work out to be nice numbers, some of them don't, but I'd like to just use a calculator to evaluate all of these and then rewrite them in exponential form. So let me pull out my calculator here, and let me type in the log of 1,000. And if you type in the log in your graphing calculator, it knows that the standard base is 10. So let's hit enter, and hey, that's a nice number. It comes out to be 3. Now, if we write this in exponential form, that should make sense, since 10 to the third power equals 1,000. So this, again, the 3 is the exponent here. What this logarithm does is it solves to find the exponent, where if I were to rewrite this in exponential form, that's the exponent I'd need to get this value, which is the input in my logarithm. So it's kind of like this whole backwards forwards thing. Think inverses. This next one's going to be not quite so nice. So let's figure out what this is equal to. The log of 723. We hit enter here. we get to this nice number here, 2.859. Let's round it out to those last three, 2.859. So that means that 10 to the 2.859 power should equal 723. And let's just verify that, just to make sure that that jives with everything. So if we go back to the calculator and I say 10 raised to the 2.859 power, and that gets us pretty close. So that is in fact the correct number here. Yes, we rounded some things, so it's not perfect, but you can see how the inverse exponential and logarithmic kind of works together. Let's do this next example. We'll take the log of 0.001. And hey, that's a nice number too. That's a -3. So that means that 10 raised to the -3rd power should equal 0.001. And hopefully that makes sense, because 0.001 is the same thing as 1 over 1,000. So these are the thousandths place. This is 1 divided by 1,000, or this is 1 over 10 to the third. Hopefully you're seeing the connection between 10 to the -3rd and 1 over 10 to the third. That's why this works out to be a nice number. All right, let's take a look at this last example. We want the log of -100. So we'll type that in the calculator. Log of -100, and hit enter, and oh no, shucks, non-real answer. What does that mean? That means that this is not a thing in the typical log world. We are in the real mode, and all of our answers must be real numbers. This is not in the domain for my logarithmic function, and this has no answer. And think about what this means. If I were to rewrite this in exponential form, this would be 10 to some power equals -100. Last time I checked, I can't raise an exponent to any sort of number that I can think of, any real number, and get a negative value. I could take the largest negative number, 10 to the -1 billionth, and all it does is just makes it a fraction, or it makes it a fraction that's very close to 0. It doesn't actually get this thing to be negative. So this is not an answer. I cannot put a negative inside of my logarithmic function, at least no real numbers. So why don't you try the same type of thing? Here are these 3 examples. Use your calculator to evaluate them, and then rewrite them into exponential form. All right, and here are my solutions with my values and my exponential form. Hopefully this is making some sense.